So now let's talk about a callable bond and coming up with the value of a callable bond. And to some extent you've seen this before, but let's again look at the price versus yield for a bond. The idea here is straightforward. If you have an option-free bond, then what does the price yield curve look like for an option-free bond? So if you have an option-free bond, then you have a price yield curve that looks like this. But what if the bond has a call option? And let's say that the call option, the embedded call option says that the issuer can call the bond back at 102% of par. Now at very high interest rates, it is unlikely that the call option will be utilized. Hence, if I were to draw the callable bond in blue, we can say that at high prices, the value of the callable bond as well as the non-callable or option-free bond is the same. However, at very low interest rates, we know that the callable bond will not possibly have a value greater than 102. Why is that the case? The way you can think of it is, let's say you are the owner of this callable bond and you know that the issuer can call it for 102. Obviously the rest of the market knows that too, so nobody is willing to pay you more than 102 for that bond. So when the yields are very low, the probability of the bond being called becomes high, but so at very low yields, the maximum possible value of the callable bond will be 102. So essentially the value of a callable bond looks something like this, where at high yields the callable bond sort of moves along with the regular straight or option free bond, but as yields go down, then the value of the callable bond does not move with the option free bond. In fact, it only goes up to 102. So you can think of it as follows, that the call price of say 102 puts a ceiling on the value of the callable bond. In terms of interest rate risk, we say that the interest rate risk of a callable bond is lower than that of a straight bond, because at relatively low yields the slope of this line is little. So if you compare this blue line, which represents the callable bond, with the red line, 1% increase in interest rates or a small increase in interest rate causes only a small change in the blue callable bond, but it causes a much bigger change in the red option free bond. So interest rate risk lower for callable bond. Another minor point is that for a callable bond at low yields, we have something called negative convexity. So the option free bond has convexity or positive convexity, but at low yields a callable bond has negative convexity. And now the final point on this slide is that the value of a callable bond will always be lower than the value of an option free bond. And this should make intuitive sense, because as an investor you don't like a callable bond. You don't like the fact that an issuer can call this bond when it suits him. So the value of a callable bond, which is this blue bond, will be equal to the option free bond minus the call option value. So if you look at say this yield, then the point A to B is the value. So this distance is the value of the callable bond. This distance from say B to C is the value of the option. So you can see that the option free value is the distance AC. The call option is the distance BC, and the value of the callable bond is AB. Okay, this might bring back memories of geometry, but I hope it illustrates the point. So now let's look at the price yield for a putable bond. So again, let's draw our axes first. So you have your price yield. Again, I'll put a option free bond in red. So this is our option free bond. Now remember, what's a putable bond? A putable bond gives the investor the right to put the bond back with the issuer at a given price. So let's say that the bond is putable at a value of 99. Now this is good for the investor, because when interest rates go up, then what the investor can do is he can give the bond back to the issuer for 99. So clearly you can see that the interest rate risk is lower for a putable bond relative to a option free bond. However, at very low interest rates, it is unlikely that the put option is worth anything. So as I just said, when interest rates are low, then a putable bond will move along with the option free bond. However, as interest rates become high, then the value of a putable bond becomes more than the option free bond. So this is the putable bond, the red is the option free bond, and in essence this value of 99 puts a floor on the value of a putable bond. If you know as an investor that you can give this bond back to the issuer for 99, clearly that becomes the minimum possible value of the putable bond. So here a couple of points. One, as I mentioned before, the interest rate risk is lower, because if you notice here in the high yield zone, as interest rates go up, the value of a putable bond goes down by very little, and in fact there is a floor of 99 if that is the put price, whereas for the red option free bond, when interest rates go up, the decrease in value is more. So that's one point. And again, using that basic geometry that we just did before, if you have point A, B and C, the value of the putable bond is AC. So the value of the putable bond is equal to the value of the option free bond plus the value of the put option. So the value of the putable bond in this example is AC. The value of the option free bond is AB, and the value of the put option is BC. And intuitively, since investors like put option, therefore the value of the putable bond is going to be more than the value of a straight bond or option free bond at a given yield. Okay, let's come back to duration now, because it's an important concept, and let's look at a very simple example that you might get on your exam. So let's say that for a given bond, the duration is 9, and to hammer in a fundamental point, duration of 9 for this bond means that if yield goes up by 1%, the value of the bond will come down by 9%. So even though duration is sometimes written as a positive number, it is actually a negative number, because when yield goes up, value goes down, and when yield goes down, value goes up. So it should really be written as a negative number. Now, what if you are given this duration and you are told that, let's say that the yield goes up by 10 basis points, and you are asked what will be the impact on value. So clearly the first part is easy. When yield goes up by 10 basis points, you know that the value will go down, but by how much? And the answer is straightforward. If duration is 9, that means a 1% increase in yield means a 9%, approximately a 9% decrease in value. So that means 10 basis points, which is equal to 0.1% increase in yield, would mean that the value must go down by 0.9%. So 1% increase in yield, value down by 9%. 1/10 of that, so 0.1% increase in yield, that means the value should go down by 0.9%. So you should be able to do examples like this quite easily. A few definitions now related to duration. This duration measure has been around for a very long time, and one of the first people to come up with a duration measure was a gentleman named Macaulay. Hence we have a duration measure named after Macaulay called Macaulay duration, and a modified version of Macaulay duration is called modified duration. Both these measures of duration are similar. We don't need to understand exactly how they are calculated, but what we do need to know is both these measures are based on promised cash flows. In other words, when we have a bond, even if it is a callable bond or a putable bond or a bond with prepayment options, we make certain assumptions about the cash flows, and then we calculate duration based on these cash flows. The problem with this approach is that it ignores call options, put options, prepayment options. So it ignores the fact that interest rates can go up and down. So it ignores the fact that interest rates are volatile, and hence the cash flow might not end up being what is initially projected. Hence the Macaulay duration or the modified duration, it works fine for option free bonds. So for option free bonds this method is okay, but if bonds have options, then this method breaks down. So that is the big disadvantage of these methods, is that when a bond has options such as a call option, put option or prepayment option, then these methods don't work. Effective duration overcomes the limitation because effective duration can be calculated using prices from a valuation model that includes the effects of embedded options. So if you recall our formula for effective duration, it was V minus V plus divided by 2V naught delta Y. So what we are saying is that this value when interest rates go down and this value when interest rates go up can be calculated using a model that includes the impact of embedded options. Hence, the effective duration measure is better than both the Macaulay and the modified duration methods. If you are confused on the exam and you have a choice between which is better, then it would be safe to assume that effective duration is better than both Macaulay and modified. Basically the point here is that there are three possible or three major interpretations of duration. The original interpretation of duration is that it is the weighted average of the number of years until the coupon and principal cash flows are to be received. So if you are reading an old finance textbook and you notice something like duration is 5 years, then they are using this interpretation. Even in tools like Excel, duration is calculated using this somewhat intuitive approach, where for a given bond you look at the various cash flows and then you come up with the weighted average of the years until the coupon and principal cash flows are to be received. We don't need to go into the details of this mechanism. The only thing that I will emphasize here is that if you have, say, a 5-year zero coupon bond, then this method very clearly shows that the duration of this will be 5 years. So clearly the longer it takes for you to get your cash, the longer or the higher the duration. And when we use this interpretation, the duration measure comes with a unit which is in terms of time. In the CFA though, we seldom use this interpretation. Another interpretation that I have implied throughout this lecture is that the duration is the slope of the price yield curve. So just to do it one final time, so if we draw again our price yield curve, we have something like this. The duration at any given point in time is the slope, or at any given yield, is the slope of the curve at that yield. So notice that at point A, the slope is relatively low in absolute terms, versus at point B, the slope is high. So that means that at lower yields, the interest rate risk is more than at higher yields. So interpretation 2 is that duration is simply the slope of the price yield curve. And the third and possibly the simplest interpretation is that duration is the approximate price change for a 1% change in YTM. So if you are explaining this duration concept to your boss, who is not a very smart man, then probably this is the one that he will understand the best. So all you are saying is that if a duration of a bond is 3, that means that if the yields go up or interest rates go up by 1%, then the value of that bond or that bond portfolio, which has duration equal to 3, will come down by 3%. So that's it in terms of the 3 interpretations of duration. Now let's talk about a bond portfolio duration, and this is very straightforward. Let's say that you have 3 bonds, A, B and C, and the duration of A is 4, the duration of B is 5, and the duration of C is 6. What is the duration of this overall portfolio? The way we come up with this is simply the weighted average of these 3 durations. If, for example, A is 50% of your portfolio, B is 25% of your portfolio, and C is also 25% of your portfolio, then the duration of the portfolio will be simply equal to 0.5 into 4 plus this 0.25 into 5 plus 0.25 into 6. So this will give you the duration of your portfolio. A limitation of duration in general and duration here in the context of a portfolio is that it assumes a parallel shift in the yield curve. So it does not deal very well with non-parallel shifts. You will understand this concept better in level 2, but for now just memorize the fact that when we talk about duration, then YTM, so the point here is that if YTM does not change equally for every bond in the portfolio, then this becomes a somewhat approximate measure. Modified and effective convexity. So this should actually, we've just talked about modified and effective duration. The point with modified and effective convexity is almost exactly the same. When we use modified convexity, we assume that expected cash flows do not change when yields change, and this assumption is okay for option-free bonds. But if a bond has options such as call options, put options or prepayment options, then this assumption breaks, and hence it doesn't make sense to use modified convexity when you are dealing with bonds which have embedded options. If bonds have embedded options, then you must use effective convexity, which takes into account changes in cash flows due to embedded options. So essentially the exact same point that you saw earlier with effective duration. The final point in this lecture now is on the price value of a basis point. PVBP, price value of a basis point, is the change in dollar value of a bond or a portfolio for a 0.1% change in yield. So this is a 1 basis point change in yield. So if a bond has a PVBP of $50 or a portfolio has a PVBP of 50, this means that if the yield goes up by 1 basis point, then the value of the bond portfolio comes down by 50. In other words, if the yield goes up by 10 basis points, you can tell, So 10 basis points, then the value of this bond portfolio will go down by 50 into 10, which is $500. A related point is, let's say a bond has a duration, or a portfolio has a duration of 9. If the duration is 9, and let's say that the value of this bond portfolio is $10 million. So what is the price value of a basis point for this situation? The way you can look at it is, duration 9 means that for a 100 basis point change, the value, let's say that for a 100 basis point increase, the value of the bond will come down by, or the portfolio will come down by 9%, which means that for a 1 basis point change, so a 1 basis point increase, the value of the bond portfolio will come down by 0.09%. And if the total value of the portfolio is 10 million, then a 1 basis point increase will mean that the value of the bond comes down by 0.09% of 10 million, which is 0.09 over 100 into 10 million, which you can calculate. So once you calculate this number, that is the price value of a basis point for this portfolio that is worth 10 million and has a duration of 9. So that is it for this reading. As always, practice hard, do the questions in the curriculum, do the practice questions in your study notes. If you have any comments, please post them. If you like this video, please click on the like button.